Now we can get to the review documents. In Blackboard, there are two review documents, one that's set up for chapter 14 and one for 15. And they roughly coincide, actually they exactly coincide with these two chapters. But the materials have to be taken as a whole because they're all about acids and bases. And ultimately, we're talking about equilibrium. So I'm going to share the first review document for chapter 14. And that introduces the concepts of acids and bases, plus the beginning problem-solving techniques for equilibrium situations. And the follow-up in chapter 15 and further on, probably in chapter 17 for Brown, discusses buffers. And in order to understand buffers, you have to understand equilibrium. Okay, so let me share chapter 14. Here we go. Now this is the review document key. There's also one that has no answers in it you can use to test yourself. And there's also a document with worked problems. And I take each one of these and work the problem out longhand. And I do it, it was several years ago when I created it. So I used one method for analysis and solving problems. And what we may do today is when we run across any of these, you may see a difference in the way I solve the problem now as when I solved it originally. But that's all right. There's more than one way to solve a chemistry problem, usually. So I have some problems marked off on my document here, and I'm going to run through those. Let's see. The screen is shared. That's good. So let me expand it somewhat, just so I don't cover up my thumbnail. Yeah, there's my thumbnail. That's good. And I wonder if we can expand this a little bit further. Let's make it bigger. Yeah, that's better. Bigger is better for uploading to YouTube. Okay. So for this first set of sample problems, we're going to be looking at chapter 14. Okay. So I've checked off all the problems on page 1. So they must be basic problems. So let's look at number 1. Which of the following is a conjugate acid-base pair? It's important to understand what we mean in our definitions by acid-base and conjugate acid-base. Remember that when we talk about our generic acid in aqueous solution, and then we react it with a base in aqueous solution, right? So this would be what type of acid-base? This would be, this could be a, my mind's gone blank. Arrhenius, excuse me. Arrhenius acid because it has a proton. And this is an Arrhenius base because it has a hydroxyl. But if you look at it in terms of proton transfer, Bronsted-Lowry base also works. This is the proton donor. This will be the proton acceptor. So that works for both. Actually, it works for Lewis too, but we're not too concerned with that right now. So this is the acid because it has a donatable proton. This is the base because it accepts the proton. And then what happens? Well, you get the B and the A to form the salt. Right? Why did I write them in that order? Because this is the cation and this is the anion. So cation anion is BA, not AB. and the hydroxyl and the hydrogen combine to form water. Okay? Now, this is an acid-base reaction. But if we just take the acid itself, put it in water, what is it going to do? It's going to react with the water to a greater or lesser extent. But as far as our definition goes, this is the acid and water is the base because it's the proton acceptor. Right? Now we're Bronsted-Lowry only. So when you do that transfer, you get the hydronium ion, transfer this proton over here. That makes this the conjugate base of that acid. Excuse me. That's stupid. Rookie mistake. That's the conjugate acid of this base. This base forms that acid. Then what's left over here, this is the conjugate base. All right. And while we're here, what can we say about the strength of an acid base? If this is a strong acid, it wants to give up that proton readily, which means the conjugate base of that acid doesn't want that proton back. It already gave it up, it's happy. So that means if this is a strong acid, that makes this a weak base. Okay, and you can say that about bases and their conjugate acids also. If this is a weak acid, that's a strong base. If this is a weak base, excuse me, that's a strong acid. And vice versa. If this is a strong base, then that would be a weak conjugate acid. Okay, now I've danced around the barn for a while. Now let's answer the questions. What is required for a conjugate acid-base pair? First, you have to create the base from the acid to say, so that means this term here has to be exactly the same as that term. Right? That's first condition. Second condition, only one proton at a time. You lose one proton to go to that one. What if you had two? Then you would form that conjugate base out of this acid. One proton, right? This is not the conjugate base of that acid because they would have to lose two protons to get there. Right? So those two conditions are required for acid-base pair, acid-base conjugate pairs. All right, so now let's look at the problem and answer the question with these rules in mind. Okay, you have A is hydrochloric acid and OCl minus. B is H2SO4 is the acid. So the conjugate base they're saying is this one, SO4 2 minus. C is this one and this one. D is this one and this one. And E is more than one of these. So it's possible for two of them to be correct based on the choice E. All right, so let's look at them. First thing is the conjugate base of the acid, does it still have the A part intact, right? So if this is the acid part, right? Is that the same as this? No, it's not. So you can stop there. That's not a conjugate acid-base pair. How about this one? Well, yeah, this part is the same as this one. But what do you have to do to get there? To do that, you'd have to lose 2 protons. And that's a violation of the second rule. 1 proton at a time. What would be the conjugate base of this acid? That would be the conjugate base of this acid. 1 proton lost. Okay? How about this one? If this is the acid, one of those protons could be lost, and what would it give you? Well, if you take a proton out of here, right, as that, it takes the positive charge with it, right? So you're left with a neutral situation. NH3 is left behind. That is a conjugate acid-base pair. What about this one? How do you go from here to here? Well, what if you lose a proton from this acid? What do you get? Right? You lose that proton. So there it is right there. You lost the proton and you're left with this. Are those 2 equal? No, they're not. That's not a conjugate acid-base pair. So E is also wrong. There's only one of them that's right. That's C. All right, that was number 1. It only took us 10 minutes to do that one. Okay. Let's see, I better check these off so I don't double back and try to redo the same one over again. Okay, the second one, the hydrogen sulfate or bisulfate ion is HSO4 minus. I just drew that one up here for you. It can act as either an acid or a base in aqueous solution. In which of the following equations does HSO4 minus act as an acid? Right? What's required for an acid? It has to donate a proton, right? So it would have to be HSO4 minus in aqueous solution would transfer a proton over here. So you would have this left over, and you would have this. So this would be your acid. This would be the conjugate base. This would be the conjugate acid of that one. This is now your base. This is your acid. Lose 1 proton. So the reaction would be HSO4 plus water yields what? Well, this is right here, but that's wrong. You transferred a hydrogen in the wrong direction, right? This one, well, we'll come back to it. Let's find the right answer first. So we need water reacting. Here's another one with water reacting with HSO4 minus SO4 2 minus plus hydronium. D is the answer. But let's go back to A. What is A doing? A is treating the bisulfate ion as a base. It's accepting a proton. So now it would have this plus this, right? It extracted a proton and left an OH minus behind. Okay, that would be the base reaction. This would be base, that would be acid. This would be conjugate acid, conjugate base. Okay? And sometimes we need to write them that way. Right? What would this be? The acid reaction, let me write it up here again. SO4 minus plus water yields SO4 2 minus plus H3O plus. This would be a base reaction. This would be an acid reaction. So this would have a K value sub A. This would have a K value sub B. Right? And the expressions would be completely different. Right? The Ka value would be this one times that one divided by this one. And that one doesn't count, right? It's a pure liquid. So it doesn't, so it'd be this equilibrium concentration times that one divided by this one. How about this one? This one would be that concentration times this concentration divided by that one. Right? See how different they are. Now, we've proven that they're related, but they're not reciprocals of one another. Okay, that was 2. How about 3? Which of the following is the equilibrium constant expression for the dissociation of weak acid HO3, HOCl, which is what? Hypochlorous acid. Right. This is hypochlorite. OCl minus is the hypochlorite polyatomic ion. When you add a proton to it, it makes it acid, and ites become us's, so it's hypochlorous acid. All right, when it dissociates, and what we're going to do now is abbreviate the reaction. We're going to say this yields this plus this. Right? And of course, you know, and I've explained that to you before, that never happens, not in real life. Protons are never floating around free. They're always attached to something. And if you're putting in an aqueous solution, that's attached to a water molecule. But for convenience, we can write it this way, and the equilibrium is going to give you exactly the same answers as if you write it the real way. So what would be the K value for this? K sub A would be that concentration times this concentration divided by this concentration. Right? And the only one that fits that is A. That's the true one right there. Now, okay, the way you look at this, see, this B answer is only these two right here. Right? I don't want you to get this one confused with B. This was part of C. Okay? Excuse me. That's part of the C answer. So that's why B doesn't work. C doesn't work either. In fact, C is inverted. If you wrote this reaction backwards, then you would use C. But then it wouldn't be an acid dissociation. It would be the inverse. Right? It would be K to the minus 1. That's the way we would write that. But that's not the one we're describing. And of course, this bottom K is just ludicrous. I mean, you don't have any oxygens in there. Right? No oxygen ions free there. You don't split up the OCl. That's a polyatomic ion right there. Right? It stays together. It does not split apart like this says it does. Okay, that was 3. How about 4? Let's see, what are we going to do with 4? Which of the following is not true for a solution of hydrogen hydroxide, 25 degrees, that has a hydroxide concentration of 2.5 times 10 to the minus 6 molar, okay, is not true. So that tells me that the way the selections are given, there's only one false answer in that whole thing. So this would be 4. And what are we getting at here? It looks like we're making statements about acidity, basicity, hydrogen ion concentrations. It's a mix, right? So if we have a hydroxide concentration equal to 2.5 times 10 to the minus 6th molar, right? What can we say about the hydrogen ion concentration? Right, what's the formula for that? Well, the K value for water is 1 times 10 to the minus 14. And that's equal to OH minus times H plus. Right? So if we know what this one is, right there, we can solve for that unknown. All we have to do is divide this one by that one. Correct? So let's see, 14, change the sign, there we go. And we're going to divide it by this number, 2.5 exponent, 6, change sign. So I get 4 times 10 to the minus 9th. For the hydrogen ion concentration, 4 times 10 to the minus 9th. Okay, now what can we say? There's no indication of pH calculation here, so we've probably done everything we need to do. Now we can take them one at a time, A through E, and answer them. A, Kw equals 1 times 10 to the minus 14th. Does that change? It's a constant. It never changes, except with temperature. And we're saying the solution is 25 degrees, so yeah, that's valid. A is true. It's a constant. How about the solution? Is it acidic? Well, look, what's required for acidic solutions? The hydrogen ion concentration must be less than 10 to the minus 7. Greater than 10 to the minus 7, excuse me. That's a lot less than 10 to the minus 7th, isn't it? Right? 10 to the minus 9th. Or you can look at it this way. The base concentration is greater than 10 to the minus 7th, so it makes the solution basic. So B is false. It's not acidic. It's actually C. Solution is basic. And the hydrogen ion concentration is, in fact, 4 times 10 to the minus 9th, which makes D also true. And then Kw is independent of what the solution contains. Exactly. Kw is the dissociation constant for water. So it doesn't matter what you put into it, it's still there. That reaction happens always. With pure water, with any aqueous solutions, it's always there. Okay. 4. Let's see what's next. Oh, okay, that must be important because we're going to the next page and working every one of them. Number 5. Okay. All right. HA and HB are both weak acids. Okay. HA and HB, they're both weak acids. right? So they have a dissociation constant that's less than 1. But HA is stronger than HB, right? So what does that say about the Ks? The K for HA versus the K for HB. The K says that if this one is stronger than that, then the K must be bigger, right? Because of the way that K is written, it favors product, and product has protons in it plus conjugate bases. So this K must be larger than that K. All right, what else can we say? Well, if we say this yields this plus that, and we say this one yields this plus that, we know that this is the acid and that's the conjugate base. This is acid and that's conjugate base. And if the strength is different, that means this side is favored more than that side. Okay, we know that based on what's given. So let's see, which one of these statements is correct? All right. A minus is a stronger base than B minus. First of all, there's more to that statement, but is that true? If that's not true, then we throw it out. A minus is a stronger base than B minus. If the acid is stronger, if this is a stronger acid than that one is, then the base of this one is stronger than the base of that one. See, it's just the other way around. Acid stronger than acid, base stronger than base. So A is false. We don't have to go any further. How about B? B minus is stronger base than A minus. That's true. If this is a weaker base, a weaker acid, then the base, conjugate base, is stronger than A minus. So that part is true. Let's see if the rest of the statement is true. Which is a stronger base than water? Which is a stronger base than chloride? Well, it doesn't take much to be a stronger base than chloride because all weak acid conjugate bases are stronger than chloride. Why? Chloride is derived from HCl, hydrochloric acid, which is a strong acid. So chloride is going to be a very weak base. So that means that actually both of these bases are stronger than chloride. But how about water? Is B minus a stronger base than water? We're not given any values here, right, to compare, right? Because what's the K? The KW for water is 10 to the minus 14th. Right? So that means that this is a very, very weak acid, which makes the base very strong. What is the conjugate base of water? That is a very strong base because this is a very weak acid. All right. So what can we say about B minus is stronger than A minus? That's true. Is it a stronger base than water? Well, yeah. Because if this is an extremely strong base, then the acid is much weaker. And if you view water as a base, does it accept protons? Well, no. The hydroxyl accepts protons. Water doesn't accept protons very well. Right? Because this is the strong base, so water behaves as a weak base, H2O. So with that reasoning in mind, that makes water a weak base. If this is a very strong base, then water molecule is a weak base. And also, how do we know that? Because the reaction, if you say this is acid and this is base, then it's going to produce this and this. And the equilibrium says there's almost none of this, right? 10 to the minus 14, the equilibrium says that this is almost non-existent. 10 to the minus 14th is a very small number, which means not only is this a weak acid, it's also a weak base, because transfer of a proton from here to here is not desirable. So that means both the acid and the water are weak acid base, respectively. In fact, they're so weak that they would be weaker. This base would be weaker than either one of those bases. That's why B is the answer. I'm not even going to go through C and D, because B is the closest thing we've got to the correct answer. All right, how about 6? All right, a solution in which the pOH is 12.1 would be described as what? All right, let's make some room. Okay, and this is 6. What are we given? We're given a solution of a pOH at 12.1. Okay, and the question is it acidic, basic, or neutral? Right, we can take these one at a time. A, B, C, D, and E. C is neutral. Let's start with neutral. What would the pOH be if it were neutral? It'd actually be the same as the pH. pH of 7 is neutral, and the pOH times the pH has to be 14, so pOH would be 7. That's not 7. So it's not neutral. Now, is it slightly acidic or very acidic? What would it have to be even acidic at all? The pOH well, let's say what's the pH? It's easier to reason this if we know pH. What would be the pH? pH is equal to 14 minus 12.1, which is what? 1.9? There we go. Now that's easier to answer. Slightly acidic would be something close to 7, like 6. 1.9 is very acidic. In fact, the OSHA regulations, Occupational Safety and Health Administration, classify anything of that pH, actually less than 2, or is it 2.5? 2.5. Anything less than 2.5 is corrosive. So that is very acidic. Let's say D is very basic, slightly basic. Well, it can't be both. If it's acidic, it can't be basic. And to be basic, the pOH would have to be less than 7. pOH would be less than 7. So neither one of those can be right either. We found the correct answer. All right, that was 6. How about 7? Which of the following indicates the most basic solution? Okay. So in order to do that, it probably would be instructive to convert everything to pH. Right? What is the pH of A? Well, if the hydrogen ion concentration is 1 times 10 to the minus 10 molar, what would be the pH of that? It would be negative log of that value, right? So since that's 1, we can just focus on this one. That would be 10. pH 10. Okay, that's basic, right? We don't know how basic it is by comparison because we haven't done the others. B, POH, is 6.7. So the pH would be 14 minus 6.7, which would be what? 7.3? All right. That's only slightly basic. How about C? Okay, OH minus is 7 times 10 to the minus 5th. So negative log of that would be POH. Let's do that. 7 exponent 5, change the sign, take the log. If I can find it, here we go. And then change the sign. So that's 4.2. 4.2 POH. So we subtract that from 14, and we get 8 here and 9 there is pH. What I'm trying to do is compare apples and apples. So if we convert everything to pH, then we can make a prediction about whether it's acid, basic, and how much. So this one pH is 9.8. How about D? Well, the pH is given there. pH equals 4.2. That's acidic. And at least 2 of the solutions are equally basic. Well, is that true? Well, if they're equally basic, they'd have to be equally acidic too. That's the way the calculation is done. 4.2, 9.8, 7.3, 10.0. E is false, can't be. Now we can decide which one is the most basic, which means which one has the highest pH. Let's see, there's 10, 7, 9, 4. All right, A. It has the highest pH, it is the most basic. All right, number 8. Okay. All right, 8. What's the question? Which of the following solutions contains the strongest acid? Okay. When we're talking about strength of an acid, the concentration doesn't matter. When we talk about strength of an acid, we're talking about how well does it donate protons. So that means the strength of the acid depends on how large is the K value, the Ka. A large Ka means a stronger acid. But we also, in our discussions in the lectures, discovered that if it has 2 acidic protons and the Ks are very far apart, in this case there are 10 to the minus 5, right, versus 10 to the minus 12, those are very far apart. The controlling dissociation is the first one. So we only have to look at the first one. So let's look at the size of the K values. That will tell us which one is stronger. Right? Which one is the smallest one? Right? A. HCN has 10 to the minus 10th. 10 to the minus 8th, close second, hypochlorous acid. 10 to the minus 5th is a little stronger, but here's another 10 to the minus 5th. Which one of these is stronger? Well, you look at the other part. You look at the coefficient, 7.9, 1.8. Right? 7.9 times 10 to the minus 5th is larger than 1.8 times 10 to the minus 5th. So B, this one is a stronger acid than that one. But which one's stronger than all of them? 10 to the minus 4 is a larger K value than any of them. Hydrofluoric acid is the strongest acid in this group. We didn't have to do any calculations because we read the problem and saw what the question was. Strongest acid. It didn't say what the concentration was. It said which one is the strongest acid, and in chemical terms, that requires only an investigation of the K value. All right, so I didn't have to write anything up for that one. We can figure that one out just looking at the problem. Number 9. All right, so I can do this without flipping to the next page. There we go. Which of the following statements are true? Let's see, am I going to need to write one something up here? Let's read the question and see. Which of the following statements are true? So we have to look at each statement, and we see that there are 3 independent statements, A, B, and C, and then there's composite statements for D and E. At least 2 of the statements are true, or all of the statements are false. So we've got to investigate each one, A, B, and C, to see if D or E applies. All right, so what about A? The pH of a strong acid is always lower than the pH of a weak acid. What does the pH mean? Negative log of the hydrogen ion concentration. All right, so if we do that calculation, what determines the pH? The concentration of the hydrogen ions, not the strength of the acid. Because if the strong acid is very dilute, then it may produce fewer protons than a weak acid that's very concentrated. So that makes A false. The pH of a strong acid is always lower than the pH of a weak acid. No, that's false. You can get a very, very low pH with a weak acid and a very high pH with a strong acid, relatively speaking. I think I mentioned before, we could buy 100% acetic acid in bottles. It's called glacial acetic acid. I guarantee you that the pH in that solution is going to be low enough that it will eat your skin right off the bone. But hydrochloric acid or sulfuric acid, they're strong acids. But if they're like 0.01 concentration, then they're not going to be, they may be irritating to a cut, but they won't damage your skin. How about B? The pH of a solution can never be negative. Really? That's simply a mathematical formula, right? If you put the right number in there, you could end up with a negative pH. For instance, what if we had, hydrogen ion concentration of 1 times 10 to the first power, right? 1 molar. Is it? No, 10 molar. Oh, let's just keep it easy. What if it's that? Just say it's 1 molar. Now let's make it 10. 1 times 10 to the first power will be 10 molar, right? So what's the log of 10? Well, 10 to the first power is 10. That's the way you interpret logs. So this part would be 1 with a negative sign. pH is equal to -1. So that just proves that you can have negative pHs. They don't mean much, right? But it's a mathematical calculation, just like anything else. That wasn't A, that was B. Right? So that statement is false. The pH of a solution can never be negative. No, it can be negative. How about C? What can we say about C? For a conjugate acid-base pair, Ka equals 1 over Kb. We talked about that a little earlier. Can't be. There's no way. Ka is this expression. So what's the Ka for that? The Ka would be A times H plus divided by HA. All right. What's the conjugate base here? A minus, correct? That's the acid for this expression. The base for that expression would be A minus, and it would have to react with water to produce HA plus OH. So Kb would be HA times OH minus divided by A minus. Now, what would be the reciprocal of this one? That's what this says. What's the reciprocal of that one? The reciprocal of that one would be A minus over HA times OH. That is not that. See? That's why you cannot use the reciprocal of one to get the other one. You have to use the correct formula. I'll show it to you in just a minute after we answer this question. So all three of them are false. So that's why E is the answer. They're all false. All right. In the lecture part of the course, we proved how to find Kb from Ka. The relationship is Kw, Kw equals Ka times Kb. So if you want to find Kb from Ka, you say Kb is equal to Kw divided by Ka. That's how you get Kb from Ka. That's their relationship. It's not an inverse relationship. It's this formula and this formula only. Okay. So let's see. I don't have any on the next page marked. Well, I don't have any more marked, so I'm falling down on the job. So let me look. I'm just going to have to wing it. Let's go to the next page and say, which one of these have we not talked about? We can do 10. It just reinforces the definition of Kb. So for Kb, what needs to be there? You need a base to react with water. That's how you determine Kb. So what's a base? A base is a proton acceptor. If you put something in there that will not accept a proton, or that is not reactive with water, then you throw that one out, right? For this one, this complex ion, this hexahydrate of zinc, there's nothing for it to react with, right? So even though it's got a proton over here, that's not the Kb expression. If you put a water molecule in there and transferred that proton to this water molecule, yeah, then you could call it a Kb expression. But that proton wouldn't be sitting out there. It would be attached to a water molecule as a hydronium. So that Kb, that's not a Kb expression. How about this one? Cn minus plus H plus. That's not either. That's not a water molecule. That's a free proton, which it really isn't. It's part of a hydronium. Notice that if you flip it around, HCN yields Cn plus H plus. That's the inverse of the Ka. That's not the Kb. How about C? Okay, there we have the conjugate base of hydrofluoric acid reacting with water. Okay, so far so good. Transfer a proton from water to HF, to F minus, and makes HF, and you have left over OH minus. That will give you a Kb expression. Chromium and water, that's just the formation of a complex, not a complex ion, that's a, I hate it when that happens. Brain freeze. It doesn't answer the question. Let's put it that way. How about 11? Let's see. Do we need to look at that one? Okay. Well, this is hammering that anvil a little more. Which one of these is a stepwise dissociation of H3PO4? Which of the following is not a conjugate acid-base pair? Well, do they all have the dissociation of aqueous H3PO4? Remember, you got to have the A minus is got to be the same on both sides, and then the one proton leaves. So if we go from HPO4 2 minus to PO4 3 minus, that's an acid-base pair. It lost one proton, and you got PO4 on both sides, right? So the question says, which one is not a conjugate acid-base pair? So A is, how about H3PO4? Lose one proton, you get H2PO4 minus. That's true. No problem there. H2PO4 minus loses a proton, and you get HPO4 2 minus. That's true. How about H2PO4 minus and PO4 3 minus? To do that, you have to lose two protons. Can't be. Right? It won't happen. Now, in the dissociation of H3PO4, what else do you have? Well, for any of these reactions, whatever that happens to be, it has to react with water and produce that. Correct? So this is the base. This is the conjugate acid. Okay? So this is not an acid-base pair. It's going the wrong direction, H3O plus and H2O. Well, actually, no. This is an acid-base pair, but it's flipped. Right? This is the acid, that's the base. So in effect, that is true. In the dissociation of H3PO4 or any of its other components that we've looked at, this would happen as an acid-base pair if you go in that direction to that direction. So E is technically true, which means that the only false one is D. All right. Let's see. Is 13 something new? Well, which of the following is true about the pH of a solution of sulfuric acid? Well, let's look at it. If a solution is dilute, the pH cannot be calculated. You can calculate the pH about any solution, dilute or concentrated. I mean, it's just mathematical. So A is false, right? And we're looking for the true one. So how about B? Is it false? If the solution is dilute, the pH is completely controlled by the first dissociation. Yes. If the solution is dilute for sulfuric acid, the pH is completely controlled. Not completely. It's dominant by the first dissociation, but not completely controlled. All right, so B is technically false. We know that the dominant dissociation is the first one. But the pH can be controlled, can be partially controlled by the second dissociation. So that one's false. It's not completely controlled by the first. It's not completely controlled by the second either. If the solution is concentrated, the pH is partially controlled by the second dissociation. Well, actually the pH is dominated by the first dissociation. So D is also false in its particulars. How about E? If the solution is dilute, the pH is partially controlled by the second dissociation. Well, yeah, that's true. That's not a good question. I hope I didn't put one like that in the exam. It's difficult to reason through that one without exact numbers. So let's look at 14. We'll just set 13 aside now. If 14 is useful, which of the following 0.01 molar solutions has the highest pH? The highest pH, which means the lowest hydrogen ion concentration. Well, let's see. Can we reason this one? The highest pH. Well, this is carbonic acid made from carbonate, and this is acetic acid made from acetate. So okay, so we're going to look at 0.1 molar solutions of different combinations. Right, so we need to look at these individually. So how about A? HOAC. If it's 0.01 molar solution. And then B is NaOA. It's NaOAC, 0.01 molar solution. They're all 0.01 molar, aren't they? Yeah. And then C is sodium carbonate, same concentration. And D is carbonic acid, same concentration. And E is sodium bicarbonate. All right. So let's look at this logically first. If we're looking for the highest pH, we can throw out the acids. The pure acid concentrations, they're going to be acidic pHs, less than 7, right? And we know that the sodium salts of these others are going to be on the basic side. Remember the rule of thumb, strong base, weak acid combinations give you basic solutions. So sodium hydroxide combined with acetic acid gives you a basic pH. Sodium hydroxide and carbonate, the carbonic acid, gives you a basic pH. And sodium bicarbonate, which would be the first dissociation of H2CO3. All right, so we can throw this one out, and we can throw that one out. Okay, now let's look at the K values for the first K values for acetic acid and carbonic acid. This means that the HOAC is a stronger acid than carbonic acid in its first dissociation. So that means if it's a stronger acid, it's going to make a weaker base, right? So any combination that puts OAC minus in solution is going to produce a weaker base. It's going to be a weaker base and produce a lower pH than one that has a stronger base. So this is a weaker acid, makes a stronger base. Let's look at it this way. What is this one derived from? And that's the abbreviation for acetic acid. I didn't mention that before. OAC. AC means acetate, and they stick that O out there to show you that there's an oxygen that the hydrogen attaches to. This is the acetate ion. Okay, that's what that means. So it's going to produce this plus this. Okay, if this is a stronger acid than this one, it's going to produce that one plus HCO3 minus. Okay. And just compare these two. Which one is the stronger base? Well, if this is a stronger acid than this one, then that's a weaker base. This is strong acid, weak base. This is a weaker base than this one, right? So this is not going to produce the most basic solution. It's a weaker base because that's a stronger acid. Strong acid, weak acid, strong base, weaker acid, stronger base. So this one's stronger. That means that we can throw this one out. It will not produce the strongest solution. Now we have to compare this one and this one. Right? So this one is derived from this reaction. Okay, so what is this one going to do? Well, on its first, when you put that in solution, it's going to strip a proton off of water and make this, but then this was going to strip another proton off of water and make that. Why? Because these dissociation constants are heavily weighted toward this side, and then that side. So this reaction is going to go, this reaction is going to make for extraction of more protons from water at the same concentration, which means it makes more hydroxyls, right? If you strip more protons from water, you get more hydroxyls. So this one's going to be the most basic solution. I hope that explanation was sufficient. All right, so let's see if we need to labor. Let's see. Well, I'm gonna check my time. 2:59. Okay, I need to move along. So let's, we're going to have to skip some. Let's see. We can make some rough approximations for these, 17, 18, 19. We don't have to spend a lot of time on them to answer the questions. That's what I mean. All right. So if we've got a salt of sodium and nitrate and we add it to water, what's the rule of thumb for that one? If the salt is derived from a strong base and a strong acid, you get a neutral solution. So that's why the answer here is C, neutral. How about this one? Rule of thumb. Sodium carbonate is derived from a strong base and a weak acid. Carbonic acid is weak. Sodium hydroxide is strong. So you're going to have a basic solution. The answer there is B. How about this one? Oops, there. Solid ammonium acetate. Okay, you've got ammonium hydroxide as the base source and acetic acid as the acid source. Okay, so for the ammonium, the Ka is 10 to the minus 10th. For the conjugate base of acetic acid, the Kb is 5.6 times 10 to the minus 10th. Which means that the ammonium is just as strong or weak, as the case may be. It's just as weak as an acid as acetate ion is weak as a base. They're identical, which means that this solution will be neutral, right? The competition here is for protons, and the competition is equal, right? If, for instance, we had an acid here that was 10 to the minus 5th, and the base was like 10 to the minus 7th, then the acid side would win out and produce fewer hydroxyls, more protons, and the solution would be acidic. But if the Kb were 10 to the minus 2, and the Ka for the acid part was 10 to the minus 10, then the base would win, and your solution would be basic. All right. So, okay, here's an example. Solid ammonium perchlorate, right? Ammonium has a Ka of 10 to the minus 10. No, excuse me, the Ka for perchlorate ion. Let's see. No, Ka for is 10 minus 10. The Kb is 10 to the minus 21. Okay. We can use a rule of thumb for this one. Ammonia is a weak base. Perchloric acid is a very strong acid. So the combination of the two will be an acidic solution. We don't even have to look at the K values. In this case, the Ka wins, right? The Ka is 10 to the minus 10th. The Kb is 10 to the minus 21. So the Ka wins. So you can do it either way. You can use the actual numbers to compare, or you can use the rule of thumb, which says ammonia is a weak base, and perchloric acid is a very strong acid, so your solution will be acidic. Okay? Either way works. Let's see. Which of these listed below is most important in determining the strength of an oxy acid? Remember an oxy acid? It's a polyatomic. but always oxyacids are polyatomic. So if we say HClO4, HClO3, HClO2, and HClO. The only difference between these acids, or among these acids, is the number of oxygens. And the strength increases that direction. Right? So we can use that to inform answer on this question. Which factor listed below is most important in determining the strength of an oxyacid? The size of the molecule? Well, the size does change, but that's not the factor. The ability of the molecule to change atomic orientation? No, that's kind of ludicrous. The identity of the central atom in the molecule? It has an influence, right? Chlorine versus bromine versus iodine will be different strengths, but the strength of an oxyacid is primarily determined by the number of oxygens that are present in the molecule. That's the key. All right, let's see if 23 has something to be taught here. Basic aqueous solution. Okay. This references, well, it's a mix of things. P4O10. Here we have an anhydrous acid, because both phosphorus and oxygen are nonmetals. So when you rehydrate them, you produce an acidic solution. Why? Because the P4O10 extracts hydroxyls from the water molecule and leaves behind hydrogen ions. So that would be acidic. KCl is derived from a strong base and a strong acid. That's neutral, so it won't be basic. CO2, right? You dissolve CO2 in water. It acts as a proton acceptor and leaves behind hydroxyl. So CO2 dissolved in water will be, no. That's like P4O10. That's an anhydrous. So it would produce an acidic solution like this. It actually produces H2CO3. Right? So there's the two hydrogens. There's the extra oxygen right there. And carbonic acid, we know, is acidic. How about NH4Cl? Well, that's a weak combination of a weak base, strong acid, makes an acidic solution. So all of these make acid solutions. That's why E is the answer. None of those make basic solutions. Let's see. Which one of these will not produce a basic solution? Will not produce a basic solution. Well, there's your anhydrous acid, SO2, that makes acid. Ammonia dissolved in water produces ammonium ion as the conjugate acid, and OH is the conjugate base. So that's basic, definitely. BaO, this is a basic anhydride, and they're always formed from metals and oxygen, or metals and nonmetals, usually oxides. So that would produce a basic solution. This would produce a basic solution. All it would have to do is dissociate hydroxyls. You got it. So the only one that does not produce a basic solution is the first one. It produces an acidic solution. All right, so we can look at one of these. Yeah. Which of the following species cannot act as a Lewis base? All right, so we need to redefine. Lewis acid, base. So a Lewis acid is an electron pair acceptor. And a base is an electron pair donor. Okay? Which one cannot act as a Lewis base? A donor. Oxygen ion? Oh yeah. They have those extra ions up here available. This one has ions available. Right. How about this one? H2S. Can it act as a Lewis base? Oh, cannot act as a Lewis base. Can H2S donate an electron pair? There's your electron pairs. It can donate these pairs to a hydrogen and accept the hydrogen. That's the Lowry-Bronsted definition. So this hydrogen can come in here like that, form a bond, and you form the SH3 plus ion. So H2S can act as a Lewis base. How about NH3? Can it act as a Lewis base? Oh yeah. NH3 can accept a proton, right? And the proton comes over with no electrons, right? Leaves them behind, which makes OH minus here. So that proton comes over, and how does it bond with ammonia? Well, ammonia looks like this. So that proton comes in, and the ammonia donates an electron pair. It's a base. So the only one that doesn't act as a Lewis base is methane. Why? Let's look at it. Methane is like this. Right? Hydrogens, all the hydrogens are duets. The carbon has its octet, 2, 4, 6, 8. It has no pairs to donate. Not going to give them up. So it will not act as a Lewis base. All right. So you can follow that same reasoning for those other questions. There's some others in here. Lewis acid, Lewis base. I threw this one out because it was dumb. It was messed up. Let's see. Let's see if we can tell in this reaction. 29. I know I'm going to have to go over into overtime, which there's nobody here, so it doesn't matter. I'll just keep talking and finish up the discussion. So in this reaction, calcium oxide plus, and that's solid, plus SO2, that's a gas, yields calcium sulfate. Solid? Salt, and not sulfate, sulfite. Calcium sulfite. Okay. So which one donates electrons and which one accepts electrons? Well, what do we have here? Well, this solid is a crystalline matrix of calcium and oxygen ions. like this. Okay? And this one is this is an ionic compound, so you can treat these as separate ions. But this is a covalent compound, so it has to be treated together. So what's happening? Well, let's look at the charges. Right? This one, shoot, my mind's gone blank again. Oxidation states, that's what I was looking for. Oxidation state here is 2 minus and 2 plus. What about this one? The oxidation state here is 2 minus. The oxidation state here, since they're 2 times that is 4 minus, this has to be 4 plus. Okay? All right, what is it over here? Well, that's 2 plus. This is 2 minus, which makes 6. 6 minus total. So what does sulfur have to be? Well, let's see, 4 plus. So the oxidation states didn't change, so we can't say that. But the reaction does occur, so we've got to say something about electron transfer. All right, which one donates electrons? That would be the base, correct? This one cannot donate electrons, right? It's a positive ion. This one is our Lewis base because it can donate electrons even though the oxidation state stays the same. Those electrons can be donated in a reaction to this species. And this species is covalent. So we don't look at it as ions. So we have the electron pair donated over here to that one. This is the Lewis acid. It's the electron pair acceptor. And it produces that compound. All right, so which one matches that? O2 minus acts as the base and SO2 acts as the Lewis acid. That's true. All right. So let me take a quick look at my hard copy and see what's coming down the pipe. Let's see. Okay. Let's do 37. We might come back to 36, but I definitely want to get 37 in here. Okay. And we're still in chapter 14 of my textbook. The question is, what's the equilibrium concentration of H2PO4 minus in a 0.202 molar solution of H3PO4? All right, so we're going to have to use some equilibrium math here. What's the reaction? The reaction is H3 H2PO4. I'm going to leave out the aqueous because it's all in aqueous solution. And it's in equilibrium with H plus H2PO4. One minus, excuse me. One minus. There we go. Okay, and the Ka for that dissociation. And remember what we said about these. The pH is controlled predominantly by the first dissociation. So we don't have to calculate the successive ones. If we only want to find out, well, actually, we're not looking for the pH. We're looking for the concentration of this, which is fine. We do both calculations at the same time, actually, and you'll see that very readily. Okay, so H3PO4 dissociates here, and the K value for that one is H plus times H2PO4 minus divided by H3PO4. Okay, so what's the initial concentration here? We just put H3PO4 in solution. So its concentration is going to be 0.202 molar. How about these two? When we first put it in, their concentration is approximately 0. Right? We know there are some hydrogens in there, but they're due to the autoionization of water, and they're very low concentration. So what's the change? Well, we're going to add some of this and some of that, right? And we're going to subtract it from this side because it's 1 to 1. For every one of these, you lose one of those. Oops, sorry. Getting ahead of myself. Minus X. So now the equilibrium concentration is 0.202 molar, let's see, minus X. And here is X and X. So when we plug those into the equation, we get X squared, because these are equal, X and X, divided by 0.202 minus X, and that's equal to 7.5 times 10 to the minus 3. Okay. Now, if we want to avoid the quadratic equation, we might have to say something like, is X really so small that it will not influence that term? And you look at the K value is 10 to the minus 3, right? 1,000th of a molar. Dissociation. So it probably is much less. We can do the calculation and see what we come up with. Maybe run the 5% rule. So what we get is, in this case, is 7.5 times 10 to the minus 3 times 0.202 equals X squared. See, I moved this one over here, and we're saying that that one doesn't matter. So now we need this times this, take the square root. And then take the square root. 3.89 times 10 to the minus 2. Molar. Now that's both hydrogen ion concentration and dihydrogen phosphate concentration. The problem is that maybe it doesn't meet the 5% rule. So how do you do that? How do you figure that one out? Well, we're going to need some space. All right, so let's move this, that. Let's plug this x into here and see if that calculation gives us that value. Right? So we have x squared would be 3.89 times 10 to the minus 2 squared over 0.202 minus 3.82 times 10 to the minus 2. Actually, you can look at this comparison. Is that a significant number? This is 2 times 10 to the first power. This is 3, almost 4, times 10 to the second power. That's a significant amount. So that's why that this answer is probably not right. If we do the calculation, then we can see if it's within 5% of the K value. 3.89, 292, that broke. Let's try that again. Square that one. Let's see, square. Here it is. Right. And then we take it and subtract it from 0.202. And then we divide that into the previous number. That's 9.28 times 10 to the minus 3. Right? What's the difference? 10 to the minus 3, 10 to the minus 3, we can ignore that and say 7.5 subtracted from 9.28 is 1.79, and then divided by 7.5 times 100. See, that's 24%, right? It exceeds the 5% rule. So what do? You either use the quadratic, or you take this value, plug it into that x, and solve for this x. So in that case, this in here gives us this equation. And this is x. So now we subtract this from that. Right? And then we multiply it by this. And then we take the square root of it. 3.5 times 10 to the minus 2 and if we run the 5% rule on this one, I guarantee we're going to make it. We'll be a lot less than 5%. And what's more, there's the answer. Right? Now notice 3.9 was given as an answer. That's the tricky part with multiple choice. Because the creator of this question said, if you use that approximation, then you're going to get this answer. But it's the wrong answer because it exceeds the 5% rule. So if the student is smart enough to make that jump, they do the recalculation that we just did and find this answer. That's the true answer. For the concentration of H2PO4 minus left in solution after we dissolve 0.202 molar H3PO4. Okay? I know that took a while, but it was worth it. All right, let me check something here. 2, 3 o'clock. Okay, I got 15 minutes. Let me see. Should I go to number 36 says how much water should be added to 10 milliliters of 11.1 molar HCl so that it has the same pH as 0.9 molar acetic acid. All right. So if it's going to be the same pH as that 0.9 molar acetic acid, that means it has the same hydrogen ion concentration. So once we find the hydrogen ion concentration of acetic acid, we can use that in the calculation of the dilution of hydrochloric acid. So what we have to do first is find out what's the pH of this acetic acid solution. So we have acetic acid. Oh, and this is number 36. And it dissociates into this plus that. So our initial concentration of the acetic acid is 0.9 molar, and this is approximately 0, and this is 0. And what's the change? Well, we're going to get some here, we're going to get some here, and we're going to get 0.9. Excuse me, same mistake over again. Minus x here. So we got 0.9 minus x, x, and x. So our calculation is Ka is 1.8 times 10 to the minus 5. And then we have x squared on the top and 0.9 minus x on the bottom. Now, if our K value is 10 to the minus 5 and we have a 0.9 molar solution, is x going to affect it? Well, no. 10 to the minus 5th versus 10 to the minus 1. In this one, I think we're safe to say that x is not going to be a problem. So it's x squared over 0.9. So now to find the hydrogen ion concentration, 0.9 times that value, square root of that. And then square root. So it's 4.02 times 10 to the minus 3. Hydrogen ion concentration equals 4.02 times 10 to the minus 3 molar. And if we compare that number to this one, in fact, it is very small. I mean, even if we did the quadratic, it wouldn't change it that much. And you can do the 5% challenge to see if I'm telling you the truth, but I think our logic is sound. Okay. So now, that's the hydrogen ion concentration that we need to match with our hydrochloric acid solution. All right. Hydrochloric acid is a strong acid. So we can assume that 11.1 molar HCl is completely dissociated, which means that's the hydrogen ion concentration. And remember what we discussed and determined for dilutions is that the molarity as long as it's a 1-to-1, we can get the dilution from the molarity of the concentrated, volume of the concentrated equals molarity of the diluted, volume of the diluted. So the concentrated here is 11.1 molar. The volume is given as 10 milliliters. Now, why didn't I put liters in there? Because molarity is moles per liter. Because this is a ratio. The volume cancels out. So you can use any volume measure here you want, and your answer is going to be in those units. So what's the molarity of the acid of the diluted? It's this one, 4.02 times 10 to the minus 3. And the dilution volume is going to be this. Now be careful. That's the total volume of the diluted solution. How much water do you need to add? Aha. That's the next step. So let's find out what this total volume is, right? We can't go any further without that anyway. It's this times that divided by that. So that's, if I did this right, 2.76 times 10 to the minus 4th. No, 10 to the plus 4 milliliters. What's that? Okay. What's our volume to start with? It's 10 milliliters. So we need to subtract 10 milliliters. Let's see if that even makes a difference. No, it doesn't. I think I made a calculation error. Let me check this again. 11.1 molar, 10 milliliters. Now, is this correct? That's the problem. Let me see if I can remember that calculation. 1.8 times 10 to the minus 5 times 0.9. Take the square root. Okay, I did that calculation correctly. Then if we say 11.1 molar, 10 mils times and divided by okay. Yeah, okay, I was right. 10 milliliters subtracted from that is still, this is over in that decimal range right there. So it's still 2.8, or, yeah, 2,760. 1, 2, 3, 4 milliliters. And subtract 10 milliliters from that is like 27599. 90, excuse me, 90 milliliters. So that's how much water we have to add. Now, how much is that in liters? Because 28 milliliters and 276 milliliters can't be the right answer. A and B are wrong. So it has to be in liters. So let's convert that to liters. 1, 2, 3. 27.59. Well, what's close to that? 28 liters. So that's why D is the answer. Okay? That was 36. Now, do we have any others? Okay, I think we can move on to chapter 15. And we're almost out of time, which is typical for me. So now we're going to be (14) and 15. Chapter 15. So I'm going to stop this share, and then I'm going to share chapter 15 key. There we go. We're going to expand. Well, where'd it go? There it is. Is that? No, that's not chapter 15. There it is. I wonder if that's shared properly. I better stop it and start it again, just to be sure. Right, so now only 15 is available for me. That's good. There we go, chapter 15. All right. This is exam 4, but for this class, it's exam 5. Excuse me. This exam says exam 4 for this class. This says exam 5, but it covers the same material. Let's boost this one up a little bit. Make it bigger. There you go. Okay. So now, we're going to carry on from where we left off. And we're probably going to be more involved in this chapter and this material with equilibrium. And in fact, buffers predominate. Okay, so let me see. We can do one. That's a fairly simple question. Scoot this back over. There we go. So this is one for chapter 15. Okay, for a solution that's equimolar in HCN, hydrocyanic acid, and, right, I can say acid because this is a solution. HCN and sodium cyanide, they're equimolar. Which statement is false? So we've got both of them in the solution together, correct? Both of those are in solution together. And we're going to say which one of these statements is false. And it looks like they're all separate statements, so one of them is false and the rest are true. This is an example of a common ion effect. Okay, how do you know? Well, there's an ion that's common to both reactants. Right there. So, when these react and we produce, actually sodium is a spectator. So what we're going to do, we're going to have cyanide ions here. And what are those cyanide ions going to do? Well, some of them are going to react with water. And that produces HCN plus OH minus. So we would put water in here as well so that we can get, it will react with this, of course, but it will also react with water. You have a coupled reaction. So you have this one reacting with water to produce that plus, well, actually, plus CN minus. And then this one reacting with water to produce that. Okay, so there is a common ion. The cyanide ion is common to both. How about B? The hydrogen ion is larger than it would be if only HCN was in solution? No, because what happens? Well, this reaction is producing these, and this reaction is producing those, and these two react with one another to produce water. So what that does is it consumes hydrogen ions or hydronium ions. That the addition of this free ion consumes hydrogen ions. So the hydrogen ion concentration is not larger with only HCN. Actually, it's less than it would be with HCN. So B is false, right? We found our false statement. The hydrogen ion concentration is equal to the Ka. Is that true? You know, that one may be false also. It's equal to the Ka only because this is equal to that, right? Remember, okay, let's erase this. Let's go to Henderson-Hasselbalch. pH is equal to pKa plus the log of the conjugate base. Well, let's stick to our reality here. Cn minus over the acid. Okay? That's true for this reaction. So we know what K is, we can calculate what pKa is. If these are equal in concentration, what does that do for the log term? This is log of 1. So what's the log of 1? 10 to what power gives you 1? 0. So this term becomes 0. The pH is equal to the pKa, which means the hydrogen ion concentration is equal to the Ka. Okay? That was easy. I thought it was going to be hard. All right. That actually was number 2. No, that was 1. Oh, we haven't finished 1. Well, we found the right answer. So what that means is C is true, B is the false one, C is true, A is true. How about D? Addition of more sodium cyanide will shift the acid dissociation equilibrium of HCN to the left. Is that true? If we add, say we have this, and we add more sodium cyanide, what are we adding? The common ion is cyanide, right? If we add more of that, then Le Chatelier says, we're going to go back this way. So it shifts the acid dissociation equilibrium, not the constant, but the equilibrium, the position shifts to the left. And it consumes some hydrogen to do that. That's why the pH tends to remain fairly stable. Okay, addition of sodium hydroxide will increase Cn minus and decrease HCN. All right, what happens if we add sodium hydroxide? The hydroxide ions react here, make water. okay? So this will decrease, and that will increase. Okay, that's true. So really, the only false one here is B. All right. My board's walking. All right. Now let's do number 2. Which one of these solutions would result in a buffered solution? Okay, at least 2 of the above could result in a buffer, so we got to do all of them. So what are we looking for with a buffered solution? The ideal buffered solution is one in which the acid concentration is equal to the conjugate base concentration. That puts you right in the middle of the buffer zone. So if we drew our pH and we add base, we're going to get a curve like this, right? There's the buffer zone. Here's the equivalence point, and the buffer is exactly 1/2 equivalence to be in the middle of the buffer zone. Buffer zone is like here. So the ideal place to be is right in the middle. That way you can add hydrogen ions, and it only shifts the concentration of the pH a little bit, or you can add hydroxyls and go to the right a little bit. So you have more play, more room to play. If you had the buffer sets for the pH over here on this right-hand side, it wouldn't be able to accommodate as much base. It could take a lot of acid. Yeah, it would take a whole lot of acid, but it couldn't take much base. So what conditions do we need? Well, we need the acid and the conjugate base. And remember what that is. You only lose 1 proton to make the conjugate base. So let's see what we've got here. Which of the following will not produce a buffered solution? Well, let's see. Sodium carbonate and acid. This one is going backwards, like that. So you're essentially titrating with acid. And 0.1 molar, 50 mils of 0.1 molar acid will titrate half of the base. So that would put it in the middle. So A would be a good buffer. How about B? 100 mils of sodium bicarbonate and 25 mils of 0.2 molar HCl. Same thing, right? 25 mils is with 0.2 molar is adding the same amount of acid as 50 milliliters here. So you're consuming half of that one. How about C? 100 milliliters of sodium carbonate and 75 milliliters of 0.2. All right, that would put you on the edge of the buffer zone. All right, you'd still be buffered, but you would be on the edge. 50 milliliters of 0.2 and 5 milliliters of 1. Let's see here, 0.2 molar, so that'd be like 100 milliliters equivalent to 0.1 here, but this is only 5 mils of 1. So what you have to do is say, all right, 50 milliliters times 0.2 is what? Right, 0.2 molar? Yeah, so that would give you 10 millimoles of base. 0.2 to the 110, yeah. And the acid would be 5 milliliters of 1 mole. 5 milliliters of 1 molar, which would be 5 millimoles of acid, right? So you're neutralizing half of your base, which is going to put you in the middle of the buffer zone. How about E? 100 milliliters of 0.1 molar sodium carbonate and 50 milliliters of 0.1 molar sodium hydroxide. What's wrong with this picture? You're mixing two bases together and expecting to get a buffered solution. It ain't gonna happen. You gotta mix a base with an acid. Okay, so E is the obvious choice for the false statement. It will not produce a buffered solution. It'll just make the existing buffered solution more basic. All right, let's see what else we can come up with here. That was 3, 4. Okay, this is a good one to look at. Say we have a weak acid, HF, in solution with sodium fluoride. So let's see, 4. So you have HF dissociating into fluoride and hydrogen ions. Okay. Now, if we add sodium fluoride to it, well, we're adding this, right? So, assuming we have a buffered solution, is in solution with dissolved sodium fluoride, so we have to assume that it's a buffered solution, or at least partially buffered. So we're adding this and we're adding that. So we've got some of both in there already, not just from the acid, but from the added fluoride. Okay, now we're at equilibrium, and what if we add hydrochloric acid? Which ion will react with the extra hydrogen ions? Right? We've already got this many, but we're going to add more of them. Right? So which ion reacts to keep the pH from changing? Fluoride. Fluoride reacts with the extra hydrogens to shift the equilibrium over here until you reestablish equilibrium and satisfy the K value for HF. So that's why C is the answer. Oh, while we're here, what if we add sodium hydroxide? Instead of adding hydrogen ions, we're adding hydroxyls. What is it going to react with? It's going to react with hydrogens to make water, which means what? We're removing hydrogen ions from the equation. That means it shifts over this direction and replaces some of those hydrogens. So that maintains the pH. All right, that was 4. Let's see if 5 is worth looking at. Yeah, it's definitional. Okay, we could do this one. Let me see. I'm just checking my work here. All right. Yeah, let's do this one. Number 6. Okay. Consider a solution that's made of 2 molar hydrocyanic acid and 1 molar sodium cyanide. And the Ka for HCN is 6.2 times 10 to the minus 2. All right, so we've got this solution mixed up, and what's the acid concentration? 2 molar, right? The base concentration, the conjugate base, is Cn minus, which is 1 molar. Right? So if we use Henderson-Hasselbalch we have the base on top, which is 1 molar, and the acid on the bottom, which is 2 molar. Okay, now we need what's pKa. Well, we've got the Ka, so we need 6.2 times 10 to the minus 10, and we take the negative log of that. All right, so let's see what that is. 6.2 to the minus 10, take the log of it. I never can find the log on this computer. Here it is. And change the sign. 9.21. Right? 2 significant figures here, 2 decimal places there. 9.21 pH. Now let's see what the questions are. Well, what the choices are. I think we probably have enough information here. The solution is not a buffer because HCN is not equal to. No, it can still be a buffer. Right? It can still be a buffer. It's not in the smack dab middle of the buffer range, but it's still a buffer. Right? This is, what do we say? The buffer range was probably plus or minus the log of plus or minus 1 would still put it in the buffer range. This is 0.5, or it could be 2 if we did it the other way around. Still be in that range. It's plus or minus, I think it's plus or minus 1 pH range for ideal buffer. Anyway, so there's our pH, and no, this is not a buffer. No, it's still a buffer. So A is false. The pH will be below 7 because the concentration of the acid is greater than that of the base. Not necessarily, because this is a weak acid. So calculating the actual pH is where we answer that question. Below 7? No, it's not. It's above 7. So we don't even have to look at the reasoning for B. We just look at the value. How about C? The concentration of hydroxyls is greater than hydrogen. If the pH is greater than 7, that means the solution is basic, and the concentration of hydroxyls exceeds the concentration of hydrogen. C is true. So E can't be right because one of them is true, and we can just ignore D. All right, that was 6. Let's see if 7 is worth going after. See, I don't have things marked for this one either. I dropped the ball there, so I'm having to wing it as we go. Which of the following solutions will be the best buffer at a pH of 9.26? Okay, how do we determine the ideal buffer zone? Well, we've got several different types of buffers, potential buffers here. We've got acetic acid and sodium acetate. That looks like it'll make a good buffer, right? Equal concentrations of acid and conjugate base. How about this one? 5 molar and 5 molar. Yep, that's a buffer too, right? It's the same species here, but the ratio is the same, 1 to 1. How about this one? The ammonia is a little trickier. Let's look at E. Let's skip the ammonia for a second. 5 molar H2C3O2 and 5 molar ammonia. Maybe we better go back to C and D. Okay, so with C and D, what do we have here? We've got the acid is NH4 added. It's the conjugate acid of the base, NH3. NH3 is a weak base, so it would qualify for forming a buffered solution if the ratios were correct. Okay? So which would make the best buffer at a pH of 9.26? Well, these were equal amounts here, right? So that means their ratio is going to produce, in the Henderson-Hasselbalch equation, C2H3O2 minus over HC2H3O2. If these are equal, that term drops out, and pH and pKa, the pH will give you the right. So what is the pKa for acetic acid, right? 1.8 times 10 to the minus 5 negative log, right? That's 4.7. That's nowhere near 9.26, right? So that would not be a good buffer for 9.26. Anything with acetic acid in it, right? A and B can't be, they're false. So we need to look at C and D and see which one of these would be a better buffer. Well, how do we do this calculation for those two? Okay. What's the pKa of the reaction? Because we're given Kb, right? We can't do pKa until we find out what Ka is. So Ka, we know, is Kw divided by Kb. So that's 1 times 10 to the minus 14 divided by, oops, sorry. Is that right? Oh yeah, I was doing it right. We need Ka, and we have Kb. Kb is 1.8 times 10 to the minus 5. So Ka is going to be 14 divided by this one. .56 times 10 to the minus 10. Okay, so the pKa is equal to the negative log of that number. And if I can find it again, here it is. 9.26. 9.26. Okay, so in this arrangement, on the top would be the conjugate base, right? Acid is on the bottom. Conjugate base is on the top. There we go. But for both of C and D, those concentrations are equal, right? So that drops out. So we only have to compare the Ka value, right? So in this case, since the concentrations are equal, they produce the same pH. 9.26 is the target, and that's what we got, 9.26. But which makes the better buffer? The one with the higher capacity, right? They may be the same pH, but the one with 5 molar ammonia and 5 molar ammonium chloride will give you a larger buffer capacity. That's why D is the answer for this one. Even though C and D are both the same pH, D gives you a better buffer. Alrighty, let's see. Moving along here. I'm way over. That never bothered me before. Okay. And this just hammers that same point home. If you make a buffer solution with acetic acid and sodium acetate, the concentrations are equal, that's a good buffer. 0.05 and 0.05 molar would make this buffer of the same pH. So what can we say about these? Well, the pH of buffer solution 1 is equal to that of the buffer solution 2. Right? pHs are not different, either one way or the other. The ratio matters to find the pH. And then, like the previous problem, the superiority of a buffer depends on its capacity. As long as the pHs are the same and the same mixture of acid and conjugate base. Okay, this is a trick question. Right, 9, I don't even have to write that one up there. Which of the following is the net ionic equation for the reaction that occurs during titration of nitric acid and potassium hydroxide? For acid-base reactions, the net ionic equation is always the same. Hydrogen ions plus hydroxyls yields water. That's the net ionic equation for an acid-base titration. Okay, this is a good one. Number 10. In the titration of a weak acid with 0.1 molar sodium hydroxide, the stoichiometric point is known to occur at a pH value of 10. Right? So we know that when we reach this point, the pH is 10. All right. So which one of these indicators would be the best to use to mark that point as an endpoint color change? Well, what do? What's the pKa for pH 10? Oh, duh. That's the pKa. pH 10 is pKa for the perfect indicator, right? So which one would be best? Which one of these gives you the pKa closest to 10? Just look at it. pKa here would be 6, 8, 11, 14. I'd say 11 would be best for the color change. That's why the answer is B. You want the pKa of your indicator to be close to the pH at which in the equivalence point is reached. And plus or minus 1, we said, was a good range. So if we're looking for 10, it's got a plus 10, plus 1 for that Ka. So it should work fine. It should work very well. These are some more of the same types of questions. Let's see about this one. Which of these pairs will produce a buffered solution? Well, here you look at A. Let me just write the number up here, 12. And we'll talk about it. Can you get a buffered solution from a strong acid and a strong base? No, it's impossible. Hydrochloric acid and sodium hydroxide will not produce a buffered solution. How about these others? Hydrochloric acid and sodium chloride. Well, the problem is one of them has to be weak, derived from weak. Hydrochloric acid for E, that's a strong acid. It doesn't matter how much chloride you throw at it, it's not going to be buffered. So A and E are false. They cannot happen. Now the ones in between, maybe, right? ammonia, you could titrate it with hydrochloric acid, and you're adding hydrogen ions to it, so you're making the conjugate acid against the weak base. That will produce a buffer if the concentrations are correct. And it looks like that possibly could do it. 0.1 moles hydrochloric and 0.15 ammonia. So it kind of stretches the buffer zone, but that would work. What are you doing? With 0.1 mole per liter of HCl and 0.15 mole of ammonia, you're actually neutralizing 0.1 of these, and you left behind a half a mole, 0.05 molar of ammonia, and now you've got 0.1 molar of ammonium ions as the conjugate acid. So that would work. Let's see, C. Would C work? Well, 0.1 moles of acid and 0.05 moles of ammonia, it's only going to take half of this to completely neutralize that ammonia. So it converts all of the ammonia to ammonium. Now you have no conjugate base for the acid NH4+. So this would not be a buffered solution. You'd be outside the buffer zone. In fact, you'd be past the equivalence point. So C is false, A and E are false. All we have to do now is say, what's D? B is a good answer. How about D? Well, there's no two of the above, so D is probably false too. We've already found a true one. But let's just look at it for fun. 0.1 molar HCl and 0.2 molar acetic acid. Is that going to make a buffer? No, because you think you're titrating an acid with another acid, it won't work. It's got to be a base and an acid. All right, so that was kind of ridiculous. B is the only good answer in this group. Okay, let's see. We could do the same reasoning for those. For this one, I want to get something that's different. 16 might be a challenge. Let's see. Huh. Okay. You know, I think I made a mistake in my work problems here. Yeah. Maybe not. All right. So if we look at 16, we're comparing a single solution that's composed of these two buffer systems. At pH 6.4, which one of the following is true and the relative amounts of acid and conjugate base present? All right. So let's look at the first one, the carbonate system. This is the one that operates in your body, by the way. It's part of the buffering system in your body fluids and blood. Okay. these two buffering systems. All right, so we have to make an assumption. If they're buffering systems, we're going to say ideal buffering systems, in which the concentration of the acid and the conjugate base are equal. So if the pKa is 6.4 for this system, then the pH will be 6.4. So this one will produce 6.4 pH. For the other one, H2PO4 is HPO4, 2- plus hydrogen. This pKa is 7.2. Okay, for this one, we can say that this concentration is equal to this concentration, right? Because the pH is equal to the pKa, so that has to be true to satisfy Henderson-Hasselbalch. For this one, the Henderson-Hasselbalch would be this pH. Well, this pH is 7.2. Right? So if we say that's equal to, what's the pKa for? No, that's not right. pH is 6.4 for both of them. 6.4. The pKa is 7.2 plus the log of, let's see, this term divided by this term. Okay? So if the pHs are equal, then the relative amounts of acid and conjugate base cannot be equal. These two are equal, but these can't be equal because they've got to adjust this 7.2 down to 6.4. This needs to be a negative number, right? So how do you get a negative number out of a log? You make this term less than 1. If you make that term less than 1, then 10 to what power is a negative number? Well, 10 to a negative power, actually. So 10 to the negative power, this would be a negative number, which would reduce this one further. So what does that mean for the ratio? That means that this one is bigger than that one. So this is larger than that. All right, so let's see which one matches. We know that H2CO3 is equal to HCO3 minus in concentration. So it could be B, it could be C. Can't be anything else. Right? That has to be true. Then we compare B and C. This one says that H2PO4 minus is greater than the HPO4 2 minus. This one says the other way around. So B has to be it. That satisfies the condition here. All right? That was 16. Let's see what else we got going for us. 16. Oops, sorry. Okay, let's do 18. Okay, this is a problem where let's see. I'm looking at the wrong one. Sorry. Here we go. 18. What we want is the final calculation for the volume of HCl. Which of these expressions is correct? All right. So here's what we need to do. We need to set up the balanced equation for the reaction. All right. We're going to do a titration of aniline, and we're not given the compound, right? So we're just going to have to use aniline in our calculation. So this is 18. So we have let's see, aniline plus HCl yields what? Calculating the volume required to reach pH. The expression is correct. Yeah. Aniline is a base. So what we're going to have is H aniline plus OH minus. Okay? Now, how do we treat this problem? This is one of those problems when you're involved in a titration and you want to find the pH resulting from the titration. You break it into two parts. First, you do the stoichiometry. Let's say we do the titration. And we go all the way to the other side. So in that case, we want to do this. One direction. So what are the conditions before? Well, it says that 100 milliliters of 0.25 molar aniline. 100 milliliters of 0.25 molar. And what's required to titrate? 0.5 molar HCl. Okay? Let's see. Yeah. What am I doing here? That's chloride. So actually the reaction only requires, chloride is a spectator. So we're really focused on hydrogen ions. So when we do that calculation, we find that the titration is going to use up all of this. So how many millimoles of this are there? A quarter of that is 25, right? Millimoles of aniline. And we need 25 millimoles of this. Okay? So what volume of hydrochloric acid would give you 25 millimoles? Well, if that's going to be equal to 0.5 molar times X milliliters, we solve for X. So X is going to be this divided by a half. So X equals 50 mils. So that's just 50 milliliters. Okay? Now what that produces is well, let's see. You know what? X is the volume in milliliters of HCl required to reach, required to reach a pH of 8. I'm sorry, we're not doing an equivalence titration. Sorry, that's my mistake. Right, so I made an assumption that was not true. We're going to add so much HCl, and it's going to give us a pH of 8. That's our target. Okay, so what do we have here? We have 0.5 times X. Right? And here we have 25. Okay, so this against that gives us what as our starting point? Right? This is going to be this is before. Now what's after? Well, we're going to use up some of this because we titrated it with that, minus 0.5 X. And this is going to be X minus 0.5 X. Well, hold on a second. No, all of this is going to be used up. It's not necessarily going to be the equivalence point, but all of this is going to be used up. There's 0 there, right? And how much of this is produced? I can't even read my own writing. Right, after the reaction, this is going to be left over, but this is, excuse me, this is, there we go. After, since all of this was consumed, it's going to produce this much in terms of that. Right, all of this goes over there. It's 1 to 1. So now we have a starting point for equilibrium. So what's our equilibrium reaction going to be? Yeah, I didn't leave myself much room, did I? I'm going to erase some of this. There's 18. I need a new marker. These things don't last very long. Okay, so the reaction then is going to be I don't think this is working out just right. Okay, we are going to have some of this left over, but now that all the acid is gone, what is there for the aniline to react with? Only water. That's it. Water is left over. So now we've got aniline There we go. I get it started. There. Now the only thing that it can react with is water. And we get an equilibrium. So this was the stoichiometry. This is the equilibrium. So what is it going to do? Well, it's going to produce some more of this. And since it extracts a proton, we're going to have OH minus. Okay, that's our equilibrium situation. Let's see, what do I want to erase? I want to be sure and get these numbers up there. All right, so now the stoichiometry was in terms of absolute moles of everything. That's what we had here. Now we need to work in concentrations for equilibrium to function. So we have 100 milliliters of aniline and some volume of HCl. That adds to the volume. So here's the volume of HCl. That means initially the concentration of aniline is going to be 25 minus 0.5 x divided by 100 plus x. Okay. I think I can erase this now. How about an H plus is going to be this one. This is our starting point, 0.5 x divided by 100 plus x. All right, and this is 0 and that's 0. All right, so what's the change? The change is going to be that much. So how much of the hydrogen ions are going to be moved? They're going to be derived from the pH. Right? pH equals 8, which is equal to the negative log of the hydrogen ion concentration. So we need to take the anti-log of negative 8. All right, so 8 change sign. 10 to the power of 8 is 1 times 10 to the minus, well, that's not right. Oh, no. Excuse me. This is OH minus, right? We're not looking for hydrogen ion concentration. Excuse me. We're looking for OH because of this reaction. That's the one that determines the pH, that amount. So what is that amount? Well, we know that the pH is 8. What's the pOH? The pOH is equal to 14 minus 8, which is what? 6. So this amount over here is going to add 1 times 10 to the minus 6th, right? Because pOH is 6. We're going to add this much over here, 1 times 10 to the minus 6th molar, and we subtract 1 times 10 to the minus 6th here, because it's 1 to 1 to 1. All right. This turned out to be a more involved problem than I thought. What's the equilibrium situation here? Well, we've got 25 minus 0.5 x divided by 100 plus x minus 1 times 10 to the minus 6th. Here we have 0.5 x divided by 100 plus x plus 1 times 10 to the minus 6th. And here we have 1 times 10 to the minus 6th. Equilibrium. Okay? Let's see. Yeah, there. No, I don't need that. There we go. Now, what was the question? What was the question? The aniline concentration. Well, we need to know the volume, excuse me, the volume of HCl, which is X, right? The volume is X. We established that early on. Okay. So if we have the KB is equal to 3.8 times 10 to the minus 8. And that's equal to this one, H aniline times hydroxyl divided by aniline. Okay? Then we have to plug in values for each one of these. H aniline is what? Here. H aniline is 0.5 x divided by 100 plus x plus 1 times 10 to the minus 6th. And then hydroxyls are 1 times 10 to the minus 6th divided by aniline, 25 minus 0.5 x divided by 100 plus x, and that's minus 1 times 10 to the minus 6. There we go. All right, so how do we simplify that thing? Well, let's see. Let's look at our choices. If we're going to solve this expression for x, and look, it's set, everything is equal except for this one, which is ludicrous. X is not hydrogen ion concentration, it's the volume. So we can throw B out right away. And everything else is set to equal to the aniline concentration. Look at the values here. This expression and this expression. Which one is equal to aniline? The denominator, aniline, equals that. H aniline times hydroxyls equals that. Right? So we can say aniline equals to this expression. Now, can we simplify this expression so it'll fit one of these down here? Well, I'm going to have to make some room. And let's see, we need some more room here. And let's see. There we go. That should be enough. So if we set aniline move back over. aniline equal to this expression, 25 minus 0.5 x over 100 plus x minus 1 times 10 to the minus 6. All right. Oh, it's easier than I thought. Here's this expression equal to aniline. Find the one that matches. Well, this expression right here is the same as minus 10 to the minus 6x, minus 6. And then we have 25 minus 0.5x divided by 100 plus x. There's your answer equal to aniline. Aniline equals this. If you know the aniline concentration, which we do, then you can solve for x. And it looks like D is the best answer for that. There's your expression right there. Let's see, let's do this. There. Okay. That was a long one. And your instructor was struggling to fork the problem and explain it at the same time. So I think it's a safe guess that if you see a problem like this on the exam, it's going to be a bonus. Because working that problem out took me how many minutes? 20 minutes at least. So I can expect it to take an hour for my students. So I'm not going to do that to you unless you want to tackle it. So it would probably, this type of problem would be a bonus. All right. Let's see. Well, this one's going to take a while to work out if we do it. 19. So let's not do 19. I wouldn't put one that complex on there as a required part of the test. All right, 20 might be worth looking at. It'll take a little work, but I think it'll illustrate a point. So 20. I got a cat asking me for supper. You're early. Another half hour, guys. So for this reaction, we want to find the best indicator for it. So what's the condition for an indicator? Remember, where's the equivalence point? If we find the equivalence point, that pH would be equal to the pKa of our indicator. Right? So we need to find the equivalence pH for this reaction. Okay? So what do we have? We're given 0.1 molar hypochlorous acid plus 0.1 molar sodium hydroxide titration. All right. Right, okay. So let's put our information up here first. HOCl is titrated with sodium hydroxide, correct? Yep. And that yields sodium hypochlorite plus water. Okay? So what's the information we're given here? 0.1 molar HOCl, 0.1 molar. And we're titrating it with 0.1 molar sodium hydroxide, 0.1 molar sodium hydroxide. So we can say with fair certainty what the volume is going to be. Well, in relative terms. These are equal concentrations. So the volume here requires the same volume there for titration. Right? Equal volumes gives you equal moles. So what's the total volume? Well, if we need the total volume, it will be 2 of that value. Okay, just in case we need it. We may not need it. So we do the titration, right? We do the stoichiometry first. That means that all of this is used up and all of that is used up. And what do we have at when we start the equilibrium process? We start the equilibrium with that, which is basically this one, and sodium and water, right? And that gives us an equilibrium where we have HOCl again plus OH minus. Okay? So for simplicity's sake, let's rewrite this. Sodium's not going to react with anything. It's only going to be the hypochlorite ion. So there we have it for our equilibrium table, or ice table. All right, so how much of this was produced? Well, the concentration of this hypochlorite ion is going to be half of that, because we neutralized it and we had to add equal volumes to do it. So this is going to be 0.1 molar divided by 2. We're going to actually cut the concentration in half because we added an equal amount of sodium hydroxide in volume. So that's why we did this, to prove that we have to cut this concentration in half. So that's where we start from here. And this is 0, and that's 0. Okay, so the reactions go in that direction. And it's 1 to 1 to 1, so we're gonna lose X here. We're gonna add X here, and we're gonna add X here. So we have 0.1 divided by 2 minus X, and we have X, and we have X. Okay? All right. So now, what kind of equilibrium do we have here? It's not the acid, it's the base, right? So we've got Ka, where is it? Ka, here it is, 3.5 times 10 to the minus 8, but we need Kb for the hypochlorite ion, right? So we've got to find the Kb. Let's see. The Kb is going to be equal to Kw divided by Ka, which equals 1 times 10 to the minus 14 divided by 3.5 times 10 to the minus 8. Right. So I just need to divide those. 3.5 minus 8, 2.86 times 10 to the minus 7. That's KB. Okay, so what does the KB look like? Well, let's make a little room here. The KB is going to be this value equals this one. Oh, no, excuse me. There we go. We're working from this equation. Almost made a rookie error again. It's going to be this one. Hydroxyls divided by OCl minus. Okay? So what are those values? This is X and this is X. So that's X squared in the numerator. And this one is going to be 0.1 divided by 2 minus X. Now, can we say that X is going to be much smaller than that value? Smaller than 0.050. Well, let's see. Let's look at this value here. That'll tell us. Look how small that value is. That X is going to be insignificant. So what we can do is say, that's gone. And now we just need to take this one times that one and take the square root of it. So 0.05 and divide that into 2.86 to 10 to the minus 7. And then take the square root. So I get 2.39 times 10 to the minus 3. X equals 2.39 times 10 to the minus 3 molar. And X is the hydroxyl concentration. That's not the answer because we're looking for a pH at equivalence to compare with the pKa of our indicator. Right? So what are we going to do? Well, the simplest way, I think, is to find the pOH and then subtract it from 14. So the pOH would equal the negative log of 2.39 times 10 to the minus 3 equals what? I already got it in my calculator, so I'll just take the log of it. I can find my, here it is. .62. 2.62. So now the pH is 14 minus 2.62, which is 11.4. Now you look for the indicator that works best in that range. And let's see, you know what? I think it's going to be a stretch, but let's see if I did the calculations right. 20. No, I did something wrong. Let me try that calculation once more. So I need 2.8. Okay. I think that's an error. Where's my calculation? This is equal to the POH. For the KB. The KB is 2.86 times 10 to the minus 6. 2.86 exponent 6 times 0.05. Then take the square root. 3.78 times 10 to the minus 4. All right, so this is wrong. There we go. And that value is 3.92, which gives you 10.1. There we go. That's better. Then you look for 10.1, and the best one for 10.1 is thymolphthalein. 10.1 is within that range. You could get by with phenolphthalein. You'll be introducing some error, but if that's the only thing you have, it would work. But thymolphthalein would work better. Okay, let's see if there's anything else that really needs to be attended. 21. Is going to take some work. 22 takes some work. 23 takes some work. All right, so we're talking about some pretty involved calculations. And this is not something that I would give you on an exam to do this extensive calculation. I would simplify it considerably. So when you're doing a titration, you have to think in terms of stoichiometry first. You start off with what are the major species, how are they going to react? And do the stoichiometry all the way to completion. Then you take those species that result from that titration and put them in as major species and say, now what reaction results? And in this last example, the reaction, we did an acid-base titration, but at the end, we had a base, a conjugate base reacting with water. So that's a base equivalence. No, a base equilibrium, pardon me. And then you do the equilibrium based on the new starting point. And that's what all of these subsequents here, all of these require that type of reasoning. How about 25? That might be worth looking at. 25. Yeah. And this is a fun problem too. All right. So let's move this. There we go. 25. All right. A certain indicator, HIN, which means indicators are weak acids. That's why it's written that way. H with the indicator part, okay, has a pKa of 9. So when it reacts, it's going to produce hydrogen ions and indicator ions. There's your acid, there's your conjugate base. And it becomes, the color becomes visible to the human eye when 7% of the indicator is in the IN minus state. Okay? So the pKa we're given is 9. pKa equals 9. What we want to know is at what pH does that color change take place? All right. So if the color change takes place at 7%, if this is 7% of that, then what we have is the color change is this one, IN minus divided by HIN equals 0.07, right? That's the decimal equivalent of 7%. So the ratio of this one to this one is 0.07. Okay, now that's everything that we're given. So how do we solve this problem? We want to know the pH when that ratio is fixed. Okay, we know that this term is 0.7. We know that this term is 9. Okay, right? This term right here is right there. So now we can solve for the pH. We just say the log of 0.07 and we add it to 9. Okay, that log is going to be a negative number, right? It's less than 1. So add 9 to that, and we get 7.85. So at 7.85, the human eye will detect that color change. The closest one is 7.88. Must be a rounding error. Actually, it's the wrong value. It should be 7.85. I wonder if I can edit that. No, wait a minute. There we go. All right. So that's all I can get away with going 45 minutes over. Actually, it's more than that. It's an hour and 20, hour and a half. So I better quit. And we'll have, this test will be next Monday. Next Friday, excuse me. So this is Friday the 26th. All right, so you add 7 to that, and you get April 2nd. April 2nd will be this one. And for this exam, and we'll jump into the next topic, which is equilibrium of complex ions. That's actually a fun chapter. Let me be sure I'm correct here. Yeah, solubility and complex ion equilibrium. So we're going to get to talk about solubility as well. And that will be the only chapter covered in the next exam. This exam covers a little bit of extra material, but it's all acids and bases. That's why I combined them both. Made sense. Okay, that's it. I'm going to stop the share and close the program because I'm all alone.